For those who have just joined in, we're waiting a few minutes so that people can join, and then we will be starting with the webinar. Okay, I think we can start, and people in any case can continue to join later. So welcome all to the third episode in a series of webinars showcasing the uses and benefits of Copernicus, the Earth observation component of the EU space program. My name is Sofia Gobin. I'm part of the Copernicus Support Office, and I'll be your moderator today. This third webinar looks at how Copernicus data can be used to study the effects of climate change on agriculture, highlighting benefits of remote sensing for monitoring the impact of climate change on agriculture, and how Earth observation can be used to make agriculture more climate resilient. I should mention that this webinar is being recorded as we speak, and it will be shared on the Copernicus EU YouTube channel. So to make this webinar more interactive, we will be using Slido for live questions. If you have downloaded the WebEx app, you will find Slido to the right-hand side of your screen in the Apps tab. If you're joining us directly from your browser, then you can use Slido through the link that we've shared on the chat. You may respond to the questions that pop up on Slido as we go, and also you may ask any questions based on the content of the presentations that we will have today. So please feel free to type in your questions so that we may answer them during the dedicated Q&A sessions after each one of the presentations. So the first thing that we want to do is to share a question with you, which is what sector do you currently work or study in? This is a bit of an icebreaker. As you respond, I will go through the agenda for today, just giving you an overview. So we will have an introduction by Tim Lemmens from the European Commission. This will be followed by two presentations from experts on the field, Samuel Almond from the Copernicus Climate Change Service, and Gobin from VITO Remote Sensing. Following each of these presentations, there will be opportunities for questions from the audience, so please feel free to type in your questions on Slido. So I see that people have been sharing their current work or study fields. Before giving the floor to our speakers, I would like to add a new question, so I'm sorry, I'm gonna deactivate this first poll. And we would like to know, how would you rate your knowledge about Copernicus on a scale from 1 to 5? So I'll give you a few moments to respond. Okay. You can continue to answer to that question, but I would like now to introduce our first speaker, Tim Lemmens. Tim is a policy officer for the Copernicus program within the Earth Observation Unit of DG DEFIS at the European Commission. He has a background in geography and on geographic information systems, as well as experience in the agriculture and fisheries domains. He's currently working on the Copernicus Land Monitoring Service, which is responsible for the pan-European services, as well as the in situ component of Copernicus. Tim, the floor is yours.
Thank you, Sophia. Okay, you should see the screen now. Indeed, hello all of you, although I cannot see you. I'll try to give you a quick introduction on the Copernicus program. I haven't seen the results of the vote or the question that Sophia just asked, but I'm sure that many of you, if not most of you, know already a lot about the Copernicus program, if not more than me. The Copernicus program is one of the key elements of the Union Space Program, which is currently written down in the EU regulation 2021-696. And the Copernicus program is an Earth observation program, which is nowadays the world leading provider of space data and information. So it's really a successful program, success story in this whole EU policy. One of the key aspects of Copernicus is indeed fighting climate change. You see the elements dealt with in the EU space program at the right hand side. Well, fighting climate challenge is really something dealt with by Copernicus. How is Copernicus established? It's a very big ecosystem of different actors and different topics. I'll try to give a quick overview. Here on the left-hand side, it starts with satellites. The Copernicus program is managing some satellites themselves, the Sentinel satellites, but is also gathering data or buying data from other parties, either national or international parties. That's called the Copernicus contributing missions. So there are two different sources coming from space, but there is also a source coming from the Earth surface, the in situ component of Copernicus, which is providing observations from the ocean, the soil, land use, weather data, and so on and so on. These observations are serving together with the satellite images as input for the whole Copernicus system. The second step is a big database. Well, maybe I should not say a database, but it's various data bases around the world. Don't think of it like something on your hard disk, because we're no longer talking in terms of gigabytes, not even in terms of terabytes, but we're talking in terms of petabytes, which is 1 million gigabytes. So several dozens of petabytes of information are managed in the Copernicus program and used further down the process. Of course, as a user, data is not interesting. You have to make information from the data. To do this, you have this second big chunk of players in the Copernicus program, the Copernicus services, which make sure that of all the data coming in, the users are getting different products, different end data through tailored processes, through procedures and various analyses. These different services can be grouped into 6 big themes. We have the atmosphere monitoring service, the marine environment monitoring service, land monitoring, climate change, emergency, and security. Most of these services provide full, free, and open data access, which means that everybody can access these data. There are some limitations or restricted data in the field of security, and in the field of security, sorry. This is how it currently is running. However, Copernicus is looking at the future, and they don't stop with the current Sentinel satellites, which are in deployment or are being deployed, but Copernicus is already looking at the future to see which new sensors and satellites should be provided. There are 6 expansion missions planned now, and of these, especially the land surface temperature service will be interesting for agriculture, and the hyperspectral mission is probably also something which will be very interesting. I will just give a few examples of how Copernicus is linked with EU legislation. For example, in the land use change and forestry regulation, the famous LULUCF regulation. I didn't invent the acronym. We are in the review of this regulation, we are trying to see how Copernicus can help and how the Copernicus data can facilitate the member states reporting on greenhouse gases, on monitoring the process and the evolution, and to support the decision making in this policy. Another regulation where the Copernicus is already clearly used and linked is the new Common Agricultural Policy, the new CAP regulation, in which, as you can see here in the last paragraph, Article 65(4)b is really mentioning that Copernicus satellite data from the Sentinels should be used to manage, to observe, to track all the agricultural activities. There are numerous other examples of where Copernicus is used for policy and implemented in policy decisions. You have ozone monitoring, air quality studies. The Arctic policy is heavily relying on observations from Copernicus. Greenhouse gas emissions, the emission trading system, the methane observatory, etc., etc. Many of these are also have a link with agriculture and with rural development. And then I still have one last slide. I could have put it as first one as well, but I thought it was a nice one to summarize the introduction. The EU Green Deal currently is a key initiative of the Commission, of the current Commission. And of course, Copernicus is contributing heavily to this policy. There are different components, many of which have linked to agriculture, and of course, Copernicus plays a big role in this as well. So I hope this was a bit of information for most of you, and not too boring for the ones that already know everything about Copernicus. Thank you.
Thank you very much, Tim, for this detailed introduction. Now, before we continue, we have another question for the audience, which is what brought you to this webinar. We're really curious to know why you wanted to join this Copernicus webinar on the impact of climate change on agriculture. And now, as you respond to our question, I will present our first speaker today. He's Dr. Samuel Almond. Samuel works at ECMWF, the interested entity implemented the Copernicus Climate Change Service, also known as C3S, on behalf of the European Commission. In his role as Sectoral Information System Officer, he manages a diverse set of contracts which aim to showcase how the C3S's climate data store and associated infrastructure can be used to deliver user-driven climate information for specific sectors. Samuel, the floor is yours.
Excellent. Thank you, everybody, for your time, and thank you very much to the Copernicus office for providing an opportunity for me to present. Now, while I find my cursor to go on full screen, that's the problem of having multiple screens here. Here we go. It's just taking its sweet time. Perfect. So as Tim mentioned, Copernicus Climate Change Service is one of the core service offerings from Copernicus. And we're focusing on the provision of trusted and free and open data related to climate change and the impacts of climate change on different sectors, one being agriculture. So many of the points I'm discussing today aren't related directly to Earth observations. We actually use Earth observations in the modeling process rather than actually serving a high resolution Earth observation data, but hopefully this will become much clearer in the structure. So there's a small introduction to Copernicus and C3S, and then I start to talk about the climate change and our agricultural offering, and then provide some key examples of actually how C3S data, Copernicus data, is being used to derive new and novel services for the agricultural sector. So the Copernicus Climate Change Service is actually a service that provides data, but also information to legislators, businesses, citizens, researchers, EU institutions. And what we do is we take information from the Earth observation program, the Sentinels, but also access to modeling information. And here, the Copernicus Climate Change Service is subtly different to other Copernicus services that really rely on Earth observations, whereas we actually include modeling information such as climate projections, reanalysis information, but also impact models to really understand the impacts of climate change on different services in different sectors. And what we do, we serve this data through the Climate Data Store, and this is like a one-stop shop for climate information. And then we create additional applications to serve different user needs. Typically, we've got about 155,000 users registered, and we have a typical download rate of 100 terabytes per day, which is a huge volume of data. And we have typically data users, which are researchers, but also information users, which require your kilobytes and your visualizations and your reports. So we cover a broad section of the Europeans, be it researchers or policies or citizens or businesses. So we provide free and open and quality and trusted information related to climate change. Now, being a remote sensing program, an Earth observation program, we do provide access to essential climate variables. An essential climate variable is been identified by GCOS, the Global Climate Observing System, as 54 variables being essential for monitoring the state of our climate. And we have information related to atmospheric physics, atmospheric composition, ocean, but more importantly, and related to agriculture, is biosphere and hydrology. On top of that, I mentioned that we also have model data, and this is incredibly important for understanding our climate, both past climate and future climate. One really critical tool for the understanding and monitoring of climate change is something called a reanalysis. And a reanalysis is essentially a weather forecast run backwards in time, but constrained with loads of different sources of information. Loads of information from in situ, loads of information from satellite sensors. And we essentially plug in the gaps with the in situ network and create this gaps without maps for the reconstruction of past weather, past climate from near real time, going way, way back to the 1950s. And this allows us to really explore the evolution of our climate from then to our current. We also have something called climate predictions. And these are initialized forecasts, and they run from present day outwards to about 7 months. And these are incredibly powerful tools for the understanding of large scale global circulation patterns and how these may impact things like temperature and precipitation at the seasonal and the 1 month to 7 month scale. And being a climate change service, we also provide access to climate projections. be it the CMIP5, which are the past runs, and also the CMIP6 simulations, which underpin the latest IPCC assessments. We also provide access to a higher resolution Eurocordex simulations, which are the downscaled global projections. And these provide more information relevant to policy and climate change assessments at the regional scale. So we've got all this information in something called the Climate Data Store, but what we're doing is also providing access to something called a toolbox. And toolbox is a scripting environment that allows users to gather different types of data within the CDS, do some computing on it, and actually create new and novel sources of information or actual applications. And here I was asked to actually introduce some of our offering for wine. We don't have anything directly, but we do have the ability to derive relevant information for wine growing. And in this case, we're looking at the Hügelin Index, which is an indicator related to the quality of wine for the Champagne region. And here we can see that climate change information from the past and the future projections is being processed to look at the suitability of the Champagne region for business as normal emission scenarios, but also high emission scenarios. So we can really start to get an assessment of whether the evolving climate is likely to impact wine production, but it could be anything. It could be cotton production, it could be specific crops, but also you're starting to get a feeling for how climate change could actually impact food security and farming practices at the regional to global scale. So this is an access page to the Climate Data Store. And here I'm just typing in agriculture, so you can actually start to see what sort of offering we do have within the Climate Data Store related to agriculture. We've got information from the past, the present, to the future, looking at different crops around the world. And we're also providing access to applications. And these applications allow users to play around with our data without actually having to download vast amounts of it. So climate change, the effects of climate is well, agriculture is one of the most climate dependent economic sectors we have. And the warming world is also creating challenges for crop production globally and in Europe especially, but also near the equator, where there's been multiple examples of crop failures with an evolving climate. Many lower latitude regions, crops like maize and wheat, have suffered from environmental changes, but further north, further from the equator, there may be some opportunities to enhance yield production. So climate change it's not an all doom and gloom across the world, and we have to adapt and understand and address these potential changes and adapt our agricultural system accordingly. C3S data can help producers identify these potential changes and help them adapt and respond to climate change in the future. So we have a dedicated agricultural service offering, and we're supporting agri-research, agri-business, and also policy, so we can start to inform how we can adapt, either be through new types of crops, so you're starting to do selective breeding, or you can start to think about how you have to evolve your irrigation systems if you know your climate's becoming increasingly drier, or there's or rainfall patterns change. So climate change information is hugely valuable to agriculture, be it at the regional basis or the global basis, to start to looking about food security and how business and commodity trading can adapt to an evolving climate. Here is a quick introduction video of our climate service offering for agriculture.
Agriculture is a very important sector. We have to provide food for the growing population in the world. At the same time, agriculture is very much under threat of climate change and increasing climate variability.
And in that sense, we are providing to people interested in agriculture a number of variables that they can feed in their crop models, so that if if you run a crop model, then you can have high quality data fitting into it, so this can improve the prediction of yields, for instance.
We try to develop these things together with our users, and one of them is the CGIR network, which is an international group of research institutes interested in crop development. And one of their main tasks is to develop crop varieties that are more climate resilient and that do better under increasing drought conditions. And in the past, these kind of organizations had to work with very coarsely resolved data. We can provide them with much more precise data for the exact location where they have their field stations, for example, where they do experiments with different seeds and crossbreed different seeds, etc.
But at the same time, we also provide top-level indicators for a number of important crops, such as wheat or maize or soybeans and the like.
That makes it, I think, very different from a lot of other efforts or providers or data sets that are around, that we are much more crop specific than normally is the case.
So on top of that, we also provide other data sets, and these data sets allow users to actually explore the potential changes in climate change up to the end of the century. And these products are based on an ensemble, which is a number of climate projections, so we can actually start understanding the range of future possibilities. And we have 26 agroclimatic indicators, and these are rather generic, like growing degree days or number of frost days, to very specific crop specific indicators related to, for example, soybeans, wheat, as well. So that's another data stream. And then we also provide enhanced Earth observation based indices. So these include your data coming from your Sentinels, but as well as the American missions and other third-party missions. And the idea is to produce a dry matter productivity data set for specific crops around the world, so we can start to understand in near real time any anomalies in yield production. And this is extremely important for food security as well. On top of that, we have a number of applications in the toolbox and published in the Climate Data Store. One of these being an application based on AgriAdapt, which was a EU LIFE project. And this allows users to explore agroclimatic indicators relevant to agricultural production in Europe under present climatic conditions, as well as comparing different future scenarios up to the end of the century. So we can look at the 1.5 degree warming world versus the 4 or 5 degree warming world, and see how vegetation and specifically crop development will change as the climate starts to evolve. And here we're looking at things such as heat stress, but also the changing regime in precipitations, for example. And these applications also allow users to see how past production and past climatic conditions are actually departing from your climate models, to actually see how well the climate models are actually predicting or showing how the current climate is evolving. So these are very useful as well. We also have been working with a number of organizations throughout Europe to develop new and novel climate services to support agriculture. Here is an example of how reanalysis information, so your past weather and climate information, can be used to develop applications to help regulate pests in the field. In this example, we're using climate information to show how biopesticides application can be used to cope and deal with locusts in various parts of the world, including China, Africa, and we've been working with an organization that's starting to develop a commercial application for the application of biopesticides. In addition, we've been working with a number of stakeholders in Kenya to utilize seasonal forecasts and climate projections to understand how season length and rain season onset can change at a seasonal scale, but also as the climate evolves to the end of the century. And here, this is really useful for decision support making on the medium and long term, and helping the Kenyan food security, but also helping the agricultural sector adapt to the challenges of climate change. In addition, we've been looking at non-food agriculture. Here we're looking at the production of timber in Scandinavia, and what we've been using here is seasonal forecasts to predict when the ground starts to thaw, so we can manage access to the timber plantations whilst the ground is frozen, to avoid degradation of the environment, but also damage to the root stock and then damage to the tree stock. So that's incredibly important added value service that we've been supporting through our seasonal forecasts. And finally, we've produced a climate application on the toolbox that is addressing the impact of climate change on the cotton industry. And we've been looking at the change in precipitation and temperature, but also the growing degrees in key areas of the world that primarily are the global producers for cotton. So that's it in a nutshell of what we're doing at C3S. I hope you found it insightful, and please let me know if there's any questions. Thank you.
Thank you very much, Samuel, for your presentation. We now open the floor to the participants to ask their questions. You can either post them on Slido, which you can find in the apps tab, or following the link we shared on the chat, or you can raise your hand and ask the question directly to Samuel to make it more interactive. Again, the Q&A is open, so you can send us your questions whilst people decide to join in. Then I have a question, because you mentioned that you work with stakeholders in different parts of the world, of course, because you have information that's useful for everyone, because obviously Copernicus doesn't focus only on what happens with the European climate, but with the climate all over the world. So are there any partnerships between C3S and other climate or environmental agencies around the world to create synergies between them?
Yeah, particularly, well, there's a number, but I think there's a really good example of how different Met agencies have been working together on a new system for seasonal forecasting. So we're working with not only your European centres, so like your Météo France and your CMCCs, but also the Japanese Met Agency, the Canadians, the Americans, and Australians, to create a truly multi-model prediction system for the seasons ahead. So that's one thing, and that's a really popular and very useful data set for food security at the monthly or the seasonal scale. But also we're working with Met services and research institutes in Africa to provide access to this information, because of unreliable internet and the need for reliable and really huge computing facilities to actually run your own seasonal forecasts and projections. But now they can access climate change information through the CDS, but they don't have to download gigabytes and gigabytes and terabytes of data. They can actually play and use these applications we've developed to actually really add value to their service offering as well.
That's very interesting. And in line with this questions, we've actually received a question in Slido, which is how many countries use this information on an operational basis? Do you know?
Yeah, I was looking at some stats yesterday actually, and we've got users from all around the world. So our primary users are Europe, but then it's closely followed by the US, China, but also we have a number of users from Africa and Asia. So it really is, as you say, there's global data sets, and the good thing about C3S and the Climate Change Service and Copernicus is that this data is freely and openly available for all. And climate data in particular has been very hard to find a very reliable source to get this information. And I think initiatives such as C3S and Copernicus are really changing how geospatial information is being used.
We have one other question, which is what fruitful links and benefits do you see from the new and even more precise positioning, such as the Galileo has?
That's a good question. I'm not really au fait with Galileo and how it can be used. I'm more, understand it can be used more for precision agriculture. But what has been discussed is the use of Galileo and location services to integrate climate change information, so you can actually start to bring in your climate information into your crop yield models, but also you can start to use Earth observations and drones, for example, to actually use location-based services for targeted interventions. So that's one way that Galileo could be used with climate information and Earth observation for enhancing services for agriculture.
That's very interesting. I don't think we have any more questions. So, oh wait, we do have one. Yes, sorry. Could you explain what is a revisit time for a satellite? I noted different revisit times for each of sentinels for each of the Copernicus sentinels.
Yep, so this is slightly deviating from the Copernicus Climate Change Service, but I would try to remember back to my days as an Earth observation scientist. So you have different sensors in different orbits with different swaths, and they're the imaging, the angle of view and the sensor configuration will really govern your revisit time. So you can typically have a revisit of daily or weekly. It all depends on the characteristics of the sensor and also the purpose of the mission as well. So if it's global monitoring, you may have a daily revisit, but if it's a high resolution satellite, you may go 2 or 3 days unless there's a constellation of satellites for your revisit time. So it all depends on sensors and the role of that specific sensor.
And we do have one more question, and then we'll continue because we have another speaker. And it's, are there plans to provide more downscale data that can also be used for local or municipality use?
Yes and no. So it's very vague here, but we have some downscaled information up to the kilometer scale in our biodiversity offering, but also we won't go to super high resolution downscaling because that's largely the remit of national Met services within Europe. So there is a trade-off between what we can provide at a regional scale for Europe and the world, and then what the Met offices do for your high resolution downscaling for things like urban applications, for example. So we do include some downscaled information, as I mentioned, Eurocordex, but also we've got some statistically downscaled Eurocordex and CMIP information in the CDS as well. So it's a bit of a mixed picture there.
Perfect. Thank you very much again, Samuel, for taking the time to join our webinar, for your presentation, and for answering all the interesting questions that we received. So now we will move on to our next speaker. Our next speaker is Professor Anne Gobin. Anne is Professor of Soil, Land and Water Management at the Faculty of Biosciences Engineering at KU Leuven, Project Manager at VITO Remote Sensing, and Editor of the Climate Research Journal. Anne has expertise in agri-environmental modeling, climate and extreme weather impacts on soil, water, crop systems, climate-smart agriculture, and land use dynamics. In fact, through the use of time series satellite and weather data, she can simulate soil, water, carbon interaction in cropping systems. In addition, she combines field observations with geomatics, time series remote sensing and modeling methods, which are then applied for the management of soil, water, and land resources from the field to catchment scale in different regions across the world. And the floor is yours.
Yeah, thank you very much for this very nice introduction. And thank you also for giving me the opportunity to present some of our work at VITO Remote Sensing and also at KU Leuven. Meanwhile, I'm trying to share my screen. And it should come on now. Yes. So if all is well, you can see my screen now, and it will soon enter presenters mode. That's right. And I'll also put a pointer up. So here we are on climate impacts on agriculture from space. So thank you very much for joining me this afternoon for this talk. And let's have a look at the climate impacts on agriculture. Now, a recent publication stated that crop losses have tripled due to extremes this century. And these extremes can be attributed to climate change. And that's a theory developed at Oxford University. So the scientific community has widely reported on the climate impact on agriculture, and particularly that of the weather extremes. And you can see here frost risk on fruit, then climate change impacts on potato production as well, and also the climate resilience of European wheat, which we found as a consortium very, very poor in general. Now, those climate impacts haven't gone unnoticed by the press, with reports on shorter fritters and dwindling beer supplies. Not very good news for a Belgian, as you can imagine. So let's have a look at what we can do with the Copernicus data. And this is a Sentinel-3 image from this summer, 2022. So that was Europe's driest summer in an estimated 500 years. We saw production losses in various crops, in rain-fed crops, of course, cereals, potato, grasslands as well. And down in the south of Europe, a lot more of these production losses in rice, maize, rain-fed cereals, and so on. So a lot of variability in rain-fed arable crop yields. Now, you do know probably that there is monitoring of agriculture by remote sensing that's been going on for a very long time, that program at the JRC, and you can see here some of these pictures using remote sensing indices. And a very, very well-known remote sensing index is the normalized difference vegetation index. And the anomaly of the normalized difference vegetation index during a certain period of time against a longer duration for the same period, that actually gives us an idea of whether the crops are doing better or the vegetation is doing better when it's green, and when it's red, you can see that these are negative anomalies, and they relate very well to the climatic water balance. But that's of course accumulating because the crop of course integrates all these anomalies throughout the crop growing season. Now, what can we do in terms of crop growth indicators? And that's through the Copernicus services, we can make use of the so-called biopaths, the biophysical variables that have been derived from Sentinel-2. And we were very happy to have Sentinel-2 because that meant that we could use satellite imagery at a very high spatial, but also at an unprecedented temporal resolution, a combination of the two, and also a higher spectral resolution. And as you can imagine, that has triggered off so many wonderful applications in the agricultural domain. And here you see an RGB image as we see it with our naked eye, and then all these derived crop growth indicators, because we can visualize infrared or the derived indicators that use infrared and infrared acquisitions across these different fields. And that enables us actually to follow our crops during the crop growing season. And that's what you can see here. So we started off with ProVAV at a different resolution. You can see here at 300-meter resolution, but the central camera would provide images at 100-meter resolution, which was already a game changer, we thought. But then with Sentinel-2, we moved up into unknown grounds. So we could actually monitor that crop performance. And soon the idea emerged, well, what if we fit a curve through that sort of greenness that NDVI stands for, or all these biophysical variables? And what if we could predict our yield from there? Then we could actually know more about crop productivity. And so we did. We did that for some arable crops. But we saw that those data-driven models with input of a crop growth indicator, that these models were actually quite crop specific. Clouds were still a problem. This is optical remote sensing, so we were done by clouds. And then, of course, we also saw that the impacts of some extreme weather events were really poorly captured. So we thought perhaps we need some other data apart from the optical data. So let's have a look at the cloud contamination problem, and that's what you can see here. And ultimately, of course, you want to arrive at this image where clouds are no longer playing a role. And to achieve that, we actually used Sentinel-1 to the rescue. Sentinel-1 to the rescue to provide us with cloud-free imagery. And so we could make use of the combination of high-resolution Sentinel-1 and Sentinel-2 for crop mapping. Not only did it improve the parcel detection across larger areas, but also it improved the crop type mapping. And we took actually advantage of that increased spectral, temporal, and spatial resolution by combining those two different types of satellites. Now, you know that crop area is very important. It's an important factor in crop production. Area is one factor, but crop productivity is the other, the so-called yield. So yield times area gives you production. And so we continued on our journey of fusing Sentinel-1 and Sentinel-2, and with the enormous help of all my colleagues at VITO Remote Sensing, we were able to fuse those two Sentinel products to actually arrive at crop performance monitoring. And that's what you can see here. So normally you would expect to have an interrupted FAPAR. So FAPAR stands for photosynthetic activity of a crop. So it's quite an important variable. And you can see here, particularly in that vegetative stage, when you see a sort of exponential growth phase, you would miss quite a number of images. But you can see that you can actually gap fill that with Sentinel-1, and that's what we did. And of course, there's a lot of AI algorithms in between to actually arrive at that smooth curve that you can see here. And that, of course, has got very many applications in precision agriculture, and that's what we are currently mining, those opportunities and possibilities. But we hadn't dealt with the extreme weather impacts. Our curve was still not always able to pick up these extreme weather impacts. Think of excess rainfall, for instance, and we had, well, recently we've been blessed by lots of extreme weather events, blessed for researchers, a lot less so for farmers, of course. And then in 2018, that's what you see here, a very dry summer. So in that series of 2016, 2017, and 2018, we had actually very different weather events. 16 very wet, 2017 a very dry spring, and 2018 a very dry summer. You can see what that does to our different arable crops. So in 2016 we had poor winter wheat yields. In 2018, dry summer, poor late potato yields. And for sugar beet it was mixed. But mostly the 2016 played a role, and to a lesser extent also 2017, depending a bit on the region. The other message I would like to give you with this slide is that actually crop diversity is very key for farmers to be resilient against the upcoming climate-related extreme weather events. So crop diversity is actually a very good strategy. Now we thought if we can include some of these weather series together with the satellite imagery, we can actually improve our models, our crop models, to arrive at crop productivity estimations. And that's of course important because you know that there are mechanisms such as insurances are very much interested, but of course also the farming industry is very much interested to have a kind of a forecast on what is going on and how early could we do that in the season. And so we set up a whole experiment looking at winter wheat, sugar beet and late potato and very many fields across the region of Flanders, Belgium. We took the series from OpenEO, a platform whereby those images are actually being made available. So through programming, we derived the curves. Here it's NDVI that you're looking at, gap filled also for winter wheat, sugar beet and late potato. We also looked at interpolated weather. And we looked for extremes naturally as well and their return periods. And then ultimately, and that's research that we're still doing at the moment, we looked at our crop water balance. So our crop water balance, actually we've incorporated that in the 2022 paper, but we're still working further on it because it actually gives us very, very excellent information. And that actually got us going and enabled us to produce the crop productivity. Now, but what does the farming world do to adapt and how do they adapt? Well, of course, water demand is very high and you can already see it in the pictures. Irrigation is what the farming world will look at. And you can see here pictures in Spain, for instance, center pivot irrigation, then also sprinkler and drip, for instance. These are common irrigation techniques. Drip is, of course, the most water-saving irrigation technique. And globally, agriculture uses quite a lot of freshwater resources, an estimated 70%. And it's actually irrigation is actually supplying 40% of the food, of the agricultural food worldwide. So that's quite a lot actually. But at the same time, we know that there is not very much on the supply side. And look at it, water supply is very low, certainly in a very dry summer. And look at all these low river discharges in 2022 last summer. So of course, in very many regions, that actually farmers are not allowed or it's even not possible to pump up water from the nearby rivers for irrigation purposes. At the same time, what we want to do with all this fleet of satellites, we would like to monitor irrigation from space as well. And quite often we get that question as well from different users, like, could you tell us what the area is under irrigation, and could you give us an estimate of above ground biomass production just as an indication? Now, if we're in the case of full irrigation throughout the season, that's what you can see on the left hand side here, then it's fairly possible to achieve that. But in cases of supplementary irrigation, it's a lot more difficult to detect, of course. Now, at the same time, we can use the tools that I've presented before. We can use that actually to monitor crop performance and to also monitor crop water demand, because look at our curve. And if we monitor that photosynthetic activity, then it gives us a kind of measure of when that crop would actually be in high demand for water or would experience a high demand for water. And that again enabled us to produce or to look further into it and to produce an additional tool. Here we looked at it further. So these are potatoes. We looked at canopy cover. We went into the field. We used a mobile phone app to look at canopy cover, and we related that also to to our Sentinel imagery, our derived F cover product, which is the cover of the soil. And so we could actually produce a curve with which we could simulate crop productivity, but we could also simulate improved water management ultimately. So by making use of these automatic weather stations and these soil sensors, that enabled us to set up a good model. So this was actually through data assimilation of various different data. Ultimately, that enabled us also to advise farmers on irrigation. And here, just prioritizing the fields that they are managing. And usually farmers manage a great number of fields. And so you can see that by these labels, they actually give you an indication of water stress. And here at 2 different times during the year, 25th of June and 3rd of September. You can see here there's still some room for irrigation. Perhaps this field would definitely be in need and would be high on the priority list of the farmer for irrigation, versus here this situation where we've actually come to a critical water stress and where irrigation may no longer help. But anyway, that application became quite popular amongst farmers. While looking at detecting bare soil and covered soil covered by vegetation, because this is actually a good measure for evapotranspiration, where the soil caters for the evaporation and the vegetation for the transpiration. But while doing that exercise, we also came across a fact that we could also detect plastics. Plastic soil cover, which is actually quite often used in horticulture. And you can see some examples here. Here a farmer is actually applying that plastic mulching, and here you can see the crops grown on that plastic mulching. Why do they do that? To achieve a favorable field water balance. And it actually results in a higher productivity and a higher water use efficiency. Of course, there are other mulches like green mulches or straw mulches and so on, crop residues. But of course, we can ask ourselves, well, how does that relate to soil health? We've got a very exciting paper on that. So we were actually quite excited by the fact that we could detect that from a Sentinel-2 images, and we could verify that then with worldview images, which are at a higher resolution. Now, here I'm taking you to a very, very high resolution, just as an intermediate. I know these are not Copernicus data, but with a drone, what we could do, and this is in search for adapted varieties. That's very, very important. If we want to face climate change, of course, we need adapted varieties. In search for these adapted varieties, we flew drones across a variety of trials, and the colleagues were able to establish an algorithm to count the years of the different wheat varieties. In the next step, and that's what we're working on now, that's of course very important. The genotype characterization, we can do that. The gene to phenotype characterization, we can do that at trial level. But then of course the challenge is to look at farmers' fields and to look at larger regions and to see whether we can also pick up the same indicators and the same crop performance across a much larger region and in farmers' farming conditions, in field conditions. And that's of course a challenge for every breeder. Will that new variety do well in different farmers' fields? And we're looking very much forward to that forthcoming hyperspectral mission, trying to actually enable us to embark more on that so-called spectral phenotyping across different farms and across different regions. Now let's go to a different scale. We're moving here to a catchment scale, and the upper sort of layers here, these 3 images, they show interpolation of actual evapotranspiration or interpolation of rainfall point time series or precipitation deficit, and that sort of what we had to do with in the earlier days. Now we're looking very much forward to couple the Sentinel-2 imagery and, for instance, look at the land use cover change here. If we could couple that with land surface temperature, we've looked further into fused products like taking the Sentinel-3 land surface temperature, fuse that with Sentinel-2 imagery to arrive at a sort of downscaled land surface temperature. But of course, we're looking forward to the forthcoming land surface temperature mission to augment that product and to actually improve that product with much higher resolutions. That will also improve our crop monitoring exercises. And that's a very interesting exercise that we did in a sub-basin here in Spain, where we looked at rainfall, evapotranspiration, and then surface runoff in relation to land use and land use change. And all these crop rotations played actually a huge role when looking at river basin flow. And that finding was crucial to actually communicate to local stakeholders, because they could do something about their cropping systems and crop rotations to optimize. And when optimizing that land cover, they could actually, that had a good influence on the local river flow. So they could actually influence the local water resources. Again, we think that the forthcoming land surface temperature mission would definitely enable a better product and a better analysis of this case study. So we're looking forward to that. So as a summary, I think for monitoring climate impacts on agriculture from space, I've taken you and we've discussed some regional trends at the catchment scale, looking at Sentinel-2, but also looking at the fusion with Sentinel-1. We've also looked at it at the field scale and how we could monitor time series for precision agriculture. Of course, there are other applications, as you can see the fields here, variable rate applications of agrochemicals would of course also be a possibility that we didn't discuss. Phenotyping, gene to phenotyping, that's also a possibility, not just at a very, very high resolution, but understanding that at a very high resolution enables us to then transfer the information to satellite imagery and what we can do further with it. Certainly the hyperspectral products we're looking very much into in the future. And then of course sensors, because sensors will enable us to understand much better certain extreme weather events, for instance. And here you can see that the automatic weather stations, but also soil sensors. So I thank you very much for listening in on this afternoon. And of course, I would also acknowledge all my VITO remote sensing colleagues, because you know that, or you can probably realize that there is a lot of number crunching going on at the background of all these applications. And special thanks also to all the funding projects and all the funding agencies that have enabled the applications. So thank you very much. I will now stop sharing my slides so that I can see you again.
Thank you very much, Anne, for your very interesting presentation. Now, again, we open the floor to our participants so that they can ask their questions, be it through Slido, through the chat, or by raising your hand. And we actually have already one question. It's from Dirk. He says, thank you for this excellent overview of Sentinel imagery applications. Which channels do you consider most effective to bring this information to the attention of farmers?
Well, actually, we have a dedicated platform for that. And thank you very much for that question, because actually it enables me to talk about it. And we call that Watch It Grow. And Watch It Grow, well, the title says it all. It's actually an application, a platform, where we bring all the data of the Sentinels together for farmers' fields, sentinels, but also meteorological information. For instance, the snapshot that I gave on irrigation advice, that's one of the sub-products that we're offering farmers to look at. So to prioritize their irrigation efforts across the fields that they manage. So that's
Thank
one
you.
application. Perhaps I can elaborate on another application. We have a more regional application, which we call the water radar. Because of course, when one farmer starts to irrigate, of course, the neighbors will also want to irrigate. And of course, there is a huge demand for that water, for the little water that is available, and how are you going to share that? So two things there. A farmer using that application, if the farmer can actually look for certain alternative water sources, not just rivers or groundwater, because usually that's forbidden when it's very, very dry during the summer. So the farmer will then look at alternative water supplies, wastewater from the food industry, for instance, or wastewater from the household use after, that is of course after treatment, wastewater treatment plants that is. And so he gets in that application the distance to his field. On the other hand, the companies that are providing water within a certain radius, they can see who their potential customers are. And actually, we've got some good examples. I'm moving again to the beer industry. So the local beer industry here in Leuven, where I'm based, so Leuven University, it's also hosting the Stella Artois EB InBev, ready beer supply for the students. But also they have a lot of water ready, and that water has actually been used by the Leuven, the so-called green service. So they were going to fetch water there for watering the different plants during that dry season. But they were also opening up the water for farmers in the vicinity. So farmers could actually go there and fetch some water for irrigation then. That's an example where a company is actually well placed for getting that sort of co-creation with local farmers. So it works in both ways, but it needs, of course, a regional approach.
Again, if people want to ask them questions, feel free to do so. In the meantime, I have a question, because you showed information, you showed data about the yield during 3 different years and the correlation with extreme weather events. And I was wondering if with data, by using weather predictions like the ones that C3S produces, can you make predictions of what the yield range could be in future years for different crops?
Oh,
obviously?
that's an excellent question, actually. I think for it depends where you're situated. I mean, if it's for the next season, say for 2023, then I think we would find that quite difficult. There would be a lot of uncertainty. But that's not to say that we're not looking at it. Very many researchers across the world are actually looking at it, because imagine the one who has that ability, the one who can do that, is actually holding the golden egg in his hands. So of course there is a lot of interest in that. Now, if we're at the onset of the season and say we are sort of a couple of weeks within the season, that sort of prediction uncertainty is actually narrowing as the season moves on. And towards the end of the season, you can more or less estimate quite well what sort of production you will have usually. And there are certain tricks, of course. It depends very much. It's very crop specific, of course. We know potato quite well, naturally, of course. And we know that at a certain stage, if we pass that stage, we can be quite confident and that with quite a good accuracy, we can predict the yields. But of course, it requires a lot of information. And the more information we've got in terms of satellite imagery, of meteorology, and also of our soils, that combination would actually provide us with quite a good idea and quite a good accuracy of yields. That's of course provided that we are in a situation where there is quite a lot of input as well, agricultural input in terms of optimization of fertilization and so on.
Sounds very interesting. I'm hoping that you managed to develop the the necessary know-how to be able to make these predictions. We have another question here, which is, could Sentinel-2 data be used for fertilization estimation?
Oh, wow, this is also a very challenging question. And that's something that colleagues of mine have been looking at, and with variable success. And I'll tell you why. It's like you would be, well, on just at first glance, you would probably say, well, if the greenness is sort of affected, then surely if you add fertilizer, then that greenness will sort of be improved. And that's a logical way of thinking about it. That is, if that greenness was actually solely influenced by fertilizers. But of course, there are other effects. Imagine diseases or plagues or whatever. Those kind of problems would also affect the greenness of a crop. And remember, with Sentinel-1, we don't see with Sentinel-2, we don't see individual plants. We see pixels of 10 by 10. So we have that sort of a more blurred view of the field. So we pick up the signal, and we can of course state, well, there is a certain it's less green than it used to be normally around this stage in a previous growing season. And that's how we will know, well, there is something going on. But it could also be water stress, for instance, and the greenness will also be lower. So it also takes a while to find out and to sort of disentangle all these different problems that a crop could experience in the field.
Thank you very much again. I don't see any more questions, and we're way beyond schedule. So
oh, sorry about that. Yeah.
No. It was extremely interesting. Okay, we have one more question. Could this data be used for the monitoring of the resilience of LULUCF sinks?
Yes, also, yes, indeed, yes, because, well, two things, of course, is the area that you can estimate quite well into different classes. Certainly, LULUCF has got quite distinguishable classes there, and biomass is the second one, and then that should give you quite a good estimate.
Thank you very much. Okay, now we thank you again for your presentation and for answering all of these questions. Now we are reaching the end of this third Copernicus webinar, and I want to thank again both of our speakers, as well as Team Lemmens from the Commission who gave an introduction. These were very interesting and engaging presentations, and we also want to thank the audience, for your participation and engagement. We hope that you learned something new today about how Copernicus can help us monitor the effects of climate change and make agriculture more resilient. If you have any other questions or comments, you can reach us via the links that I will share now on the screen. You should see them now. There you go. So again, if you have any other questions or comments, you can reach us through these links, and you see our online channels, which I invite you to follow in case you aren't already doing so, to stay up to date with Copernicus. Also, before you leave, we would like to know how useful this was for you. So for a second there you go. We're opening again the Slido poll so that you can tell us how useful you found the content of this webinar. We also remind you that since the webinar was recorded, we will be sharing it on the YouTube channel Copernicus EU. And thanks again for joining us, and we look forward to seeing you on our next webinar, and have a nice day.
Thank you. Bye-bye.
Bye.